All right, we're going to move on to 9.3. We're going to look at the complex plane, um, meaning imaginary numbers, but also in polar form. All right. If you need to pause this and take a look at this paragraph and read through it, please do that. All right. Um, and so, yeah, um, this is kind of an Algebra 2 idea in this introductory part. Um, when we see a complex polar equation, all right. Well, in this rectangular version, we're going to call it z equals x plus yi. All right, x and y are real numbers, and we know I is the imaginary portion of it. Okay. Just as a quick example, it says to plot the point z equals square root of 3 minus 1, or I'm sorry, square root of 3 minus I. And so we can actually plot this on the complex plane, all right? Along the quote-unquote x-axis is the real number, all right? And along the y-axis is the imaginary axis, all right? So this one here, square root of 3 minus I, I can actually, well, first of all, this is square root of 3 minus 1i, right? And you can tell this is in the format of x plus yi, right? So this would be quote unquote my x, and this one would be my y, right? And so I'm just going to plot that, right? X is square root of 3, right? I don't know, something like this, square root of 3. And negative 1i means it's negative 1, right? So here's my point here. Okay, that's square root of 3 minus I. All right. Now this portion, what I'm going to quickly do, all right, is because this is going to relate to another example, all right. This is the magnitude of z. Okay, the magnitude is the distance from the origin to that point, which I've written right here. Okay. So the magnitude, we're going to look at, it looks like an absolute value, right? And it kind of is, right? Because the distance is always a positive value. And so, yeah, the magnitude of z, excuse me, the magnitude of z is the distance from the origin to the point. Now, this is also in your notes. You could take a pause here and read on your own if you'd like. Okay. We say that this is in rectangular form, all right, this complex number, because we have x and y, which are rectangular coordinates. But we can also use our theta, like what we've been using this entire chapter so far, of polar coordinates, right? And we already know this relationships right here. X equals r cosine theta, and y equals r sine theta. So therefore, if we have x equals r cosine theta and y equals r sine theta, we can substitute these in for x and y. That's what we did here. So we have r cosine theta plus r sine theta times I, because of this I. And what we did was here, they both have a common factor of r, and so we take that GCF out. So that's what we have here. Okay. Now what I'm going to do is I'm actually going to connect these two, right? This is the relationship that we're looking for. Okay. So we want to say this. This is what we're looking at today. Z equals R times cosine theta plus I sine theta. All right. This is what you're going to have to know for the rest of this lesson. Now in this first example we're going to look at, we're going to take the example we started with, z equals square root of 3 minus I, and we're going to rewrite it in polar form as a complex number. All right. So this is what we're already used to in rectangular xy equation, but now we're going to change it into polar form using r and theta. and I just kind of guesstimated where this point might be. Now, I'm actually going to draw a triangle because that's going to help us much more. And you can see that I filled in the sides with what our values are from the equation, right? We know that square root of 3 is your x, and so this runs along the x. And then negative 1i, and so negative 1 goes along the imaginary axis, all right? So this is what we have right now. Now, we know that it creates a right triangle, and by Pythagorean theorem, when you work it out, okay, the hypotenuse turns out to be, in this case, 2. All right? Now, remember I said a little bit ago in the video, right, that the distance from the origin to that point, okay, is your magnitude. Okay. Now also think about when we plotted polar points, right? Remember it was the distance from the pole, or 0, 0, to that point. Remember that was the r value, right? And so the magnitude of the z is actually equal to your r value, all right? So the hypotenuse here of these triangles, because we're going to do maybe one more example here, the hypotenuse of the triangle is equivalent to the r value. So in this case, the r value is 2, all right? Okay. Now, we also need theta, right? We're going to have to figure out what theta is right here, okay? Now, I chose this example on purpose because, take a look, right? If I do, let's say, sine of theta, right? Sine of theta is opposite over hypotenuse. That's negative 1/2. If I do cosine of theta, that's adjacent over hypotenuse. That's root 3 over 2, right? Look at these values, right? These are familiar to the unit circle, okay? And so hopefully we remember these values, right? When cosine is root 3 over 2, and when sine is 1/2 or negative 1/2, we know that theta, right, is going to be quote unquote 30 degrees, okay? Now 30 degrees, we know that's in quadrant 1, but since we're in quadrant 4, right, the actual theta is going to be, in this case, 11 pi over 6, right? We're going to use radians instead of degrees, okay? And so again, because I know that if I do sine and cosine, all right, opposite over hypotenuse and adjacent over hypotenuse, then I can tell and recognize that the angle is actually from the unit circle. And so theta is equal to 11 pi over 6, all right? Now, what we have to do is, remember, we got to change this to polar form. And polar form from the last slide means that z is equal to r cosine theta plus I sine of theta, right? So z is equal to 2 cosine of 11 pi over 6 plus I times sine of 11 pi over 6. So that's what we have. We're done, right? We don't have any x and y's, right? We need r's, we need thetas, okay? Now there's a shortcut way of writing this, right? Instead of writing all of this out, the shorter version, which I am going to allow, right, is in this format here. Right here, z equals 2 cis 11 pi over 6, right? The CIS is just a shortened version of what's in the parentheses, and we write that theta angle just one time, all right? And so we're going to call this the cis, okay? So that's it right there. All right, so my next example, here's my setup. Negative 4 plus 4i is negative 4 this way and positive 4, so up here. And so here's what my triangle looks like. I know that if I apply the Pythagorean theorem, the hypotenuse here is going to end up being 4 root 2. Okay, so that's my r value. R equals 4 root 2. Now for tangent, right, you could do a couple things here, right? You could try and do sine over cosine, okay? I'm noticing that because these two legs are the same, kind of, right? I'm going to use tangent, right? Theta is equal to the inverse tangent of 4 over negative 4. Okay, and hopefully we recognize that, well, this is going to be negative 1, right? But that means if the numerator and the denominator are the same, this is a 45-degree angle, or pi fourths, right? But since we're in quadrant 2, right, we're in quadrant 2, so therefore your angle measure here is 3 pi over 4. Okay, there it is. I have my r value, right? So putting these together in polar form, this is going to equal 4 root 2 CIS 3 pi over 4. So now we're going to go the other way, right? If we're given a polar form of a complex number, then what is that going to look like as a rectangular form, right? So I have 2 CIS 5 pi 6, right? That means the r value is 2 and the theta is at 5 pi over 6. And so here's my setup with the triangle. So I know we're in quadrant 2 because 5 pi over 6 is over here in quadrant 2, which means my reference angle here inside the triangle, we know that's 30 degrees. Okay. Now, you gotta remember some special right triangle ratios. If this is a 30, 60, 90 triangle, right, if the hypotenuse is 2, then remember the shortest side is always half of the length of the hypotenuse. So in this case, that's going to be 1, right, because half of 2 is 1. And then the medium side across the 60 is the shortest side times a root 3, right? So in this case, that's negative, okay? All right, so there's my x, there's my y, right? Z is equal to negative root 3 plus 1i, or just I. So that's what it's like right there, okay? We're going to use the same ideas in this next example. So here my r value is 3, and my theta is 4 pi over 3. Now 4 pi over 3, got to think, what quadrant is that? That's in quadrant 3, so I'm going to draw my triangle like this. Now since we're in quadrant 3, 4 pi over 3, what you got to remember is that when you do 4 pi over 3, right, we know that that's going to be beyond pi, or beyond 180 degrees. How much more though, right? This is going to be 60 degrees, right? So this is quote-unquote 60 degrees here, okay? Which means this is 30, all right? Now the relationship still holds, right? If the hypotenuse is 3, the shortest side is half of that, so that's 3 halves, and this side is going to be the shortest side times root 3, all right? So there's my x, and there's my y. So z is equal to x plus yi. Z is equal to 3 halves. Now this is negative since it's going down. 3 halves minus 3 root 3 over 2i. And I made a mistake. This should be also this should be negative 2. Negative 3 halves, since it's along the x. Okay. So I'm going to review this a little bit more maybe on the next video, but hopefully you can go back and rewatch some parts of this video.